Hi everyone. Today we're going to work on graphs of exponentials and also logs. We're going to start off with exponentials, and I'm going to actually show some calculator tricks on how we can make this process go a little bit faster. So before we jump into actually graphing the exponentials, let's talk about some basic properties of these graphs. So when we're graphing exponentials, we can call the general form b to the power of x plus k. Now there are other values you're going to see in an exponential, but the b or the base and this k value are two of the more important values in terms of properties that we're going to see in the graphs. So the first one is this b value, or the base of our exponential. So if that base is bigger than 1 or greater than 1, then this exponential graph is increasing. When the exponential graph is increasing, we're going to have a horizontal asymptote. I'll talk about that in a second. And as we work our way to the right, the y values are going to be going up. So that's an increasing exponential graph. If b is between 0 and 1, then we would consider this graph to be decreasing, or we still have that horizontal asymptote. But now as we work our way to the right, the graph gets flatter and flatter. So something we've taken note of so far, but something that we can use to kind of check to make sure that these graphs match up the way that they should, based on whether or not that b value is greater than 1 or less than 1. All right, so now the other thing I just want to make note of is this k value, and something I kind of touched on here is that we have a horizontal asymptote. So with exponential graphs, we have a horizontal asymptote at y equals k. So that k value that we identified in the just general form of an equation is the location of that horizontal asymptote. So what that means is as our graph either goes all the way to the left or all the way to the right, we're going to approach this y value, or all the y values are approaching the value of that horizontal asymptote. Now, why do we get there? So why do we have a horizontal asymptote? It's because because b to the power of x. So no matter what our base is, when we think about values of exponents or values of x here, we can never get this whole thing to either be negative or equal to 0. We can get b to the power of x to be very, very small, right? If that exponent's negative, like 2 to the power negative 100, that's a really small decimal. So it's really close to 0, but not 0, and definitely not negative. So because of that, because of the values that we can get from this b to the power of x, our graph will always approach that k value. Really important that we know the equation, why we have one, and whether or not our function is increasing or decreasing. Right, so those are just some basic properties. Let's go down and jump into some examples. Now, for the most part, instead of having us memorize some rules, we're going to actually come up with values and create a table so we can get a set of points that we can go ahead and plot to then make the shape of the graph. So when we're deciding what x values to choose, it really does not matter entirely, but we want to pick values that give us a good shape of the graph. So to ensure that, we're going to identify the horizontal shift, which is this -5, right? And that -5 shifts everything right 5. Because this is right 5, we want that to be our middle point of the graph. So I'm going to put that in the middle of my table, and right 5 would mean that it is a +5. And then I'm going to do values bigger than 5, so 6, 7, and 8, and some less, so 3 and 4. So all we're going to do is we're going to take these values, plug them in the equation, and see what we get for y. So in other words, we're going to take f of 3, which equals 3, and 4 to the power of 3 minus 5, and then -8. So for the most part, we're going to grab our calculator. We're going to type in exactly what we see here. Okay, we don't need to make any changes to that. So let's find a good spot. All right. So first, you want to clear your window. If you open your calculator up and it is on like a weird kind of window, just a good button set to know is how to get to your home screen. If you look here above mode, you'll see quit. Anytime you hit second mode, that's going to bring you back to this home screen. So we're going to type in just this right side and see what it equals. So I'm going to go 3 parentheses 4, those parentheses are absolutely necessary, and to the power of 3 minus 5. Now, I can do 3 minus 5 in my head and say that's -2, but I'm going to type this all in at once. So if I do that, this is an older modeled calculator where it won't actually shift my cursor to be the exponent. It just displays the exponent button. So I need to put what my exponent is in parentheses. So that 3 minus 5 needs to go in parentheses. So the calculator knows that the exponent is whatever 3 minus 5 is. And now I'm going to subtract 8 from there and gives me a value of -7.8125. Okay, so that's going to be a way that we can do it with every calculator we see. And it'll take a little bit of time because you're going to have to do that 1, 2, 3, 4, 5 more times. But it's something that you can do with any calculator. Now, with these graphing calculators, we can actually get a full-on table of values, and we can have the calculator generate this for us. So here's how we're going to do that. The first thing that you want to make sure happens is that your table settings are set up to show you all of these X's. So if you look above window, you'll see this table settings or table setup. We're going to start there. So I'm going to hit second, table setup. It's going to ask us where we want the table to start. It does not matter. I can leave it at -6. I'm going to put it at 0 for now, but it does not matter. The next option, this is the change in table or delta table, which tells the calculator what we want our values to go up by. We want them to go up by 1s, like what I have here. So we're going to leave that as 1. The independent and dependent variables, we want these to be on auto for now. I'll eventually talk about when we might want them to be on ask. So once I'm done with these settings, make sure your calculator matches mine. I'm going to hit second mode and go back to my home screen. Now I can press graph and view the graph, and it'll show me what it should look like. Oh, sorry. Before I do that, I should type in my equation. So that's what we're going to do next after setting up our table settings, is set up the equation. So I'm going to go over here. I'm going to type in this equation exactly as I see it. So 3, parentheses 4, exponent. And again, I'm going to need this whole exponent in parentheses because I have this older modeled calculator. Now I'm going to type in x minus 5. Your variable button is right here next to the alpha button. So there's like an X, a T, an O, and an N. You want to click that. It should display an X, then -5, close parentheses, and then -8. So then we have our full-on equation, okay, of what we're trying to graph. So like I was trying to do before, I can press graph, which will show me what the actual shape of the graph is. I'm expecting it to be increasing because of the base being 4, and that's what we're seeing here. So that part's good so far. But in order for us to fill out this table, we want to see these X values. So the calculator can actually display a table. It's going to be the second option of the graph. If you see this table button, to access it, we hit second graph, and it will display a table. It's going to start at whatever we set it to start at in our table settings, which I set it to be at 0. But I need X values between 3 and 8. So I'm going to actually scroll down so I can see 3, 4, 5, 6, 7, 8. And then I can just jot these all down. And that way I don't need to type it in 6 or 7 different times. This is just a quicker way to come up with those values. So I can plot all these values: 3, -7.1825, 4, -7.25, 5, -5, 6, and then +4. 740 doesn't fit, and 8184 for sure doesn't fit. So our graph, after we connect them, something like that. Now our calculator showed us on the graph, right, that it's kind of flattens out here. It's flattening out at that horizontal asymptote. And so we're going to fill that in onto this graph. And we're going to fill that in by drawing a dashed line at -8. So we have a horizontal asymptote there. And there we've come up with the full graph. So do you need to use the table? Absolutely not. Okay, you could, of course, just plug in each one individually to come up with these points. So basically, you need to find a way that works for you using tools that you own and that you have access to come up with these Y values. I'm always happy to show you, if you come in for access time or study table, of how you can find those values using your own calculator or some other tool. The last thing I'm going to ask you to do for all these graphs is describe the domain and range. For every exponential, it is -infinity to +infinity. Now the range, we're not going to go below our horizontal asymptote. So our horizontal asymptote is going to affect the range. Now remember, we can see that in the equation, right? This -8, that's the lowest our graph is going to get to. And we will never actually get to that -8 because 4 to the power of x minus 5 will never actually equal 0. So what I'm trying to describe is that our range is from -8 to positive infinity. All right. Well, I'm going to have you all actually do number 2 on your own. So whether you're plugging in values one by one or doing the table, go and hit pause, come up with a graph here, and then you can hit unpause to see the values that you should have. And I'll give a quick explanation on to why I chose everything. Okay, so here are your table of values. Now let's first talk about how did I come up with these and how did I pick the x values? This horizontal shift of left 3 tells me my middle point. So I want that middle point to be -3. And that way I'm getting points that show me where the graph is increasing, which is off here to the left, and also points where it is decreasing, which is happening here off to the right. So that's why we always want it to be in the middle so that we get the full on shape of the exponential graph. If -3 is in the middle, I'm going basically from 0 to -5. Now, obviously, if you went like -1, -2, -3, -4, -5, -6, that's okay too. So it doesn't need to completely match this, but as long as -3 is in the middle and you're counting by ones, it should all work out very similar to what I have here. Right, and then your domain for every exponential negative to positive infinity, the range, this is the lowest it goes, -3 and all the way up to infinity. The last thing I want to mention is we can always write the equation of that horizontal asymptote, right? That equation here is y equals -3 because every point on this horizontal line has a y coordinate that is -3. Okay, that wraps it up for all of our exponential. And just to quickly summarize, you're going to graph exponentials by making a table of values, either using a calculator, or if need be, you could also do it by hand. Okay, it'll get a little messy, but you can plug in x's to come up with y. All right, let's start talking about graphs of logs. And we're going to actually go about this a little bit differently. We're not going to use a calculator for these, at least not yet. Now let's talk about some properties first. We're going to think about the general form of logs being log base b of x minus h. Like I said before with exponentials, there are other values here. There's an a and a k, but we don't really care about those in terms of just the properties that we're trying to identify. So just like before, this b value, our base, gives us an idea as the shape we should get. So if b is greater than 1, we're actually not going to describe this graph in terms of increasing or decreasing, because with logs, your range is actually going to be -infinity to positive infinity. So it's not really doing either one. There are different parts that are increasing and different parts that are decreasing, but in general, it's kind of doing both. So when b is greater than 1, this time we actually have a vertical asymptote. And so when b is greater than 1, the graph is getting steep as we go down. It kind of flattens out as we go up. So something like that. And so then if b is between 0 and 1, if this vertical asymptote, flat up here, or vertical, and then flattens out as we come down. So it's got a very similar shape to our exponential graphs, but our horizontal asymptote becomes vertical asymptote, and it's increasing in both directions. So our range is from negative to positive infinity. All right, now this line that I drew here, this is a vertical asymptote. And the vertical asymptote is in the form of x equals h. Now, the reason we get a vertical asymptote is because we can't take logs of negative numbers or 0, which makes sense, right? If I plug in h to this equation, h minus h is 0. So we're going to get really close to that value, but never actually there. So why do we have a vertical asymptote? Because you cannot take the log of negative numbers and 0, creating a domain restriction, and something we're going to, on the graph, is going to create a vertical asymptote. Okay, so let's go into how we're going to graph these logs, because we're going to do it a little bit differently. Now, if you remember back to our log notes, when we're learning about logs to start out with, we always are going to think about them in terms of exponentials because they're just an inverse of an exponential. So the inverse of a log being an exponential, remember that the base stays the same. So we're going to actually start with our base of 2 and 2 to the power of x. So this first column here, we're going to list values of 2 to the power of x based on these x values. So 2 to the power of -2 is 1/4. 2 to the power of -1 is 1/2. 2 to the power of 0 is 1. 2 to the power of 1 is 2. And 2 squared is 4. In the next column, this is where we're going to actually convert this exponential to its inverse log equation, which is log base 2 of x, which is what we're trying to graph, right? We're trying to graph log base 2 of x, but we'll deal with the 8 and the 4 here in just a second. So if you remember back to our conversation about inverses, one thing that I mentioned is the domain of our original function becomes our range, and we can just use a table for that. So these x's, or our domain of the exponential, becomes the range of the log. So these y values of log base 2 of x are -2, -1, 0, 1, and 2, which was the domain of 2 to the power of x. The y values for our exponential become the x's. So this would be 1/4, or I'm going to convert this to a decimal and call it 0.25, 0.5, 1, 2, and 4. And so we've just come up with 5 different points of log base 2 of x using its corresponding exponential. That's going to be how we're going to graph almost all of these logs until we learn how to do them on a calculator, which is down the road. Now, this last column we're going to skip for now because we're only going to use it if we have an a value or a number in front of the log that is not 1. So in this case, we actually don't need this. So we're basically all the way done. The only thing we haven't dealt with is this 8 and 4. Now, if you think back to our transformations lessons, this 8 shifts everything left 8. And one thing we did during this unit or during this lesson of transformations is when something shifted left 8, that told us to subtract 8 from all the x's. We can, of course, do that. We're not going to, but we definitely could. Same thing with this 4. That shifts everything up 4. So I could add 4 to all the y's and come up with a set of x and y's for this full-on equation. That can be a little tedious and can be a little tricky for those of us that don't quite understand how we can apply transformations to points. So what else we could do is this left 8 and up 4 is we can create what we're going to call a new origin. Now, it's not really our origin, but we're going to call it our new one and then apply the points from there. So left 8 means I'm going to go left 8 and I'm going to draw a new y-axis. I'm going to go up 4 and draw a new x-axis. So the intersection of these axes are our new origin. So we're pretending like that's 0, 0, but it's really not. It's still -8, comma 4. But by pretending like it's 0, 0, we can apply these points directly to that new origin to come up with the graph of log base 2 of x plus 8 plus 4. So 0.25 -2 tells me to go barely to the right and down 2. 0.5 -1, a little more to the right and down 1. 1, 0 is right 1 and then 0. 2, 1 is right 2 and up 1. And then 4, 2 is right 1, 2, 3, 4 and up 2. After I connect these points, we get a graph, something like what we drew up here, right? B was greater than 1, so we should see it kind of starting to flatten out as we move up. It's going to keep going down though. And there's our graph of the log. Now, just like before, right, on the exponential, we labeled our asymptote. Let's label this asymptote as well. This is a vertical asymptote at x equals -8. The last thing we're going to add in here is our domain and range, where the domain is restricted by the fact that we can't take the log of negative numbers and by the fact that we have this vertical asymptote here. So it's from -8 to positive infinity. The range for every log is negative to positive infinity. All right. So we're going to do this one more time. Basically the exact same equation. As you can see, the only difference here is now I have an a value of 3. Everything else is still log base 2. It's still x plus 8 and still plus 4. So for the most part, these first two columns are going to be the same. So I'm going to go ahead and just fill those in for us real fast. And we'll talk about how the a value is going to change our actual graph. So 0.25, -2, 0.5, negative 1, 1, 0, 2, 1, 4, 2. So remember that these values, the x's were the y's were the x's. And this last column here, this is where we're going to incorporate the a value, which is 3, and it's 3 times log base 2 of x. So what's happening here with that a value, and again, we talked about this with our transformations, is we're taking all our values of log base 2 of x and multiplying them by 3. So remember that the 3 is only affecting either the x coordinate or the y coordinate. This 3 is not being directly multiplied to the x, therefore it's being multiplied to our y values. So this 3 means to multiply the y values by 3. The x's are going to stay the same, so 0.25, 0.5, 1, 2, 4, and the y's get multiplied by 3. So negative 2 is negative 6, negative 1 is negative 3. 0 times 3 is still 0, 1 times 3 is 3, 2 times 3 is 6. And so now we have values for 3 log base 2 of x, where we're going to identify the shifts again, left 8 and up 4. Create our new origins just like we did before. And then pretend like this is 0, 0, and plot these points from there. So 0.25, negative 6, 1, 2, 3, 4, 5, 6, 0.5, negative 1, 2, 3, 1, 0, 2, 1, 2, 3, and 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And there's our graph. So not much different than the one we did above, but if you remember back to what the a value does, that'd be a vertical stretch. So it's as if we took the graph that we did in number 3, and we took those y values and we pulled them apart by a factor of 3. It does not affect the domain and range. The domain is still negative 8 to infinity. The range is still negative infinity to positive infinity. All right. Well, you should have some idea on how to graph both exponentials and logs now. For the rest of this packet, you have 8 more graphs that you need to do, 4 exponentials and 4 logs. Your assignment is to complete this and turn it in. There's not an answer key for it. You need to turn it in with the best that you can possibly do. Thanks for watching and have a great rest of your day.